In the last lecture, I introduced the problem of testing or you can say comparing the variances of two normal populations. And we had considered one particular type of hypothesis problem, that is sigma 2 square by sigma 1 square less than or equal to tau naught against sigma 2 square by sigma 1 square greater than tau naught. And the likelihood ratio test for this was derived. Now, we will consider for the same model the hypothesis H 4, that is sigma 2 square by sigma 1 square is equal to tau naught against say sigma 2 square by sigma 1 square is not equal to tau naught. Okay, so, we need not write the expressions once again. The likelihood function is given by 1 by 2 pi sigma 1 square to the power m by 2, 1 by 2 pi sigma 2 square to the power n by 2 e to the power minus sigma x I minus mu 1 square by 2 sigma 1 square minus sigma y j minus mu 2 square by 2 sigma 2 square. In the previous problem, I considered the maximization of this likelihood function over omega and omega h. Now, in this case omega h was sigma 2 square less than or equal to tau naught sigma 1 square. Now, in this new case, so let me repeat it here, the log likelihood function, the likelihood function and the log likelihood function which we need to write. So, L theta x y that is equal to 1 by 2 pi sigma 1 square to the power m by 2, 2 pi sigma 2 square to the power n by 2 e to the power minus sigma x I minus mu 1 square by 2 sigma 1 square minus sigma y j minus mu 2 square by 2 sigma 2 square. And we are having the omega is equal to mu I belonging to R and sigma I square is greater than 0 for I is equal to 1 2, and omega h is now theta mu I belonging to R and sigma 2 square is equal to tau naught sigma 1 square, and of course, both are positive. Here our theta is mu 1, mu 2, sigma 1 square and sigma 2 square. Now, as in the previous problem, the maximization of L over omega gives mu 1 head omega is equal to x bar, mu 2 omega head is equal to y bar, sigma 1 omega head square that is equal to 1 by n sigma x I minus x bar whole square. This is m here, and sigma 2 omega head square that is equal to 1 by n sigma y j minus y bar square, and as a consequence L head omega that is given by L head omega is given by 1 by 2 pi to the power m plus n by 2 sigma 1 omega head square to the power m by 2 sigma 2 omega head square to the power n by 2 e to the power minus m plus n by 2. Now, consider maximization over omega h. Now, when we consider over omega h, then the likelihood function gets little bit modified. Over omega h, L is equal to 1 by 2 pi sigma 1 square to the power m by 2 pi tau naught sigma 1 square to the power n by 2, because we are having sigma 2 square is equal to tau naught sigma 1 square when we are considering omega h. And then you have e to the power minus sigma by 2 sigma 1 square minus sigma y j minus mu 2 square by 2 tau naught sigma 1 square. So, of course, if we consider the log likelihood here, log of L, that is equal to minus m plus n by 2 log of 2 pi minus n by 2 log of tau naught plus minus m plus n by 2 log of sigma 1 square minus 1 by 2 sigma 1 square sigma x I minus mu 1 square plus 1 by tau naught sigma of y j minus mu 2 square. So, if I consider mu 1 head omega h, that will be x bar, and mu 2 omega h head, that will be y bar. However, if I consider maximization with respect to sigma 1 head square, I will get 1 by m plus n sigma x I minus x bar square plus 1 by tau naught sigma y j minus y bar square. So, sigma 2 omega h square, that will be equal to tau naught sigma 1 omega h head square. As a consequence, if I substitute these values in the log likelihood function, so we get L head omega h as I will get this value as 1 by 2 pi to the power m plus n by 2 tau naught to the power n by 2, and then 1 by m plus n sigma x I minus x bar square plus 1 by tau naught sigma y j minus y bar square to the power m plus n by 2 e to the power minus m plus n by 2. So, this is the term that we will be getting. Now, let us look at both of these terms here. We are having L head omega as this term and L head omega h as this term. So, the likelihood ratio test can then be written as the likelihood ratio test is then to reject H 4 when lambda x is less than c, which is equivalent to now we have already derived the expressions. So, I will just substitute here L head omega h, I will get this in the denominator and then divided by L head omega. So, this will go in the numerator. So, that gives me sigma 1 by m sigma x I minus x bar whole square to the power m by 2 1 by n sigma y j minus y bar whole square to the power n by 2 divided by 1 by m plus n sigma x I minus x bar square plus 1 by tau naught sigma y j minus y bar square to the power m plus n by 2 less than c. Now, we take reciprocal of this and we use the notation say u is equal to sigma y j minus y bar square divided by sigma x I minus x bar square. If we assume this, then we can rewrite this condition as 1 plus u by tau naught to the power m by 2 1 by u plus 1 by tau naught to the power n by 2 greater than say C 1. Okay. Let us assume this to be G u. Now, this function I considered in the yesterday's derivation of the test function. I will show the behavior of it here. I had assumed this term to be G u. Now, this term is same as this term here and G prime u we had calculated. So, this G prime u function then turns out to be. So, I straightforwardly take the same expression. We obtain G prime u is equal to some term which is equal to half of 1 plus u by tau naught to the power m by 2 minus 1 1 by u plus 1 by tau naught to the power n by 2 minus 1 m by tau naught into 1 by u plus 1 by tau naught minus n by u square 1 plus u by tau naught. And this we can see as G prime u, it will be greater than or equal to 0 if and only if u is greater than or equal to n by m tau naught, and it will be less than 0 if u is less than n by m tau naught. So, in fact, I can say greater here, greater here. So, G u is increasing if u is greater than n by m tau naught, it is decreasing if u is less than n by m tau naught. And G u will have minimum at u is equal to n by m tau naught. That means, the nature of this G u function will be something like this. There is a minimum at n by m tau naught. If I am plotting G u function, then it will have something like this. So, if I say G u is greater than C 1. So, suppose this point is C 1, then this is equivalent to saying that u is either less than certain number or it is bigger than a certain number. So, let me call this number say d 1 and d 2. So, G u greater than C 1 is equivalent to u less than d 1 or u is greater than d 2. So, this is the rejection region of likelihood ratio test. Now, this quantity u, that is sigma y j minus y bar square divided by sigma x I minus x bar square. So, if we consider this, we are having sigma y j minus y bar square divided by sigma 2 square and n minus 1 divided by sigma x j minus x bar square divided by sigma 1 square m minus 1. This follows F distribution on n minus 1 m minus 1 degrees of freedom. So, when sigma 2 square by sigma 1 square is equal to tau naught, that is H 4 is true, then u by tau naught, that follows f distribution on n minus 1 m minus 1. So, the rejection region is u by tau naught less than f n minus 1 m minus 1 1 minus alpha by 2 or u by tau naught greater than f n minus 1 m minus 1 alpha by 2. Of course, this is not necessary. I have taken the 2 points symmetric, but f distribution is not symmetric. So, the points may be at different places. So, this is f m minus n minus 1 m minus 1 1 minus alpha by 2 point, and this point will be f n minus 1 m minus 1 alpha by 2. So, this is the likelihood ratio test for the equality of the variances, and you can note here that this test is the same as the UMP unbiased test, which I derived for this situation. So, what we have shown here is that the likelihood ratio tests are applicable for the parameters of the normal distributions. Also, they can be applied to some other distributions where the distribution may not be of the normal type. It could be exponential, gamma, double exponential, etc. The form of likelihood ratio test is such that it is general. So, only condition is that you should be able to derive the maximum likelihood estimators for the full parameter space as well as under the parameter space, which is restricted because of the null hypothesis. Once we have that, the likelihood ratio test can be written. Now, it is a different matter that whether we can be able to derive the distribution of that or not. Now, in many cases we may not be able to derive the exact distribution. However, there is a nice asymptotic property of the likelihood ratio test, which I would like to state here. If you remember, for the maximum likelihood estimators, we stated certain conditions which we called regularity conditions. For example, the density should be differentiable, the parameter space should be a subset of an open set in the Euclidean space. We had assumed that the density function or any expectation of a measurable integrable function should be differentiable under the integral sign. So, these were the regularity conditions. Under those conditions, we had shown that the maximum likelihood estimator exists with probability 1, and it is also consistent, and the asymptotic distribution of the maximum likelihood estimator was shown to be normal. Now, under the same regularity conditions, because here we are dealing with the likelihood function. So, under the similar regularity conditions, the asymptotic distribution of the likelihood ratio test statistic can also be found. So, I will state the result without the proof here. Under regularity conditions on f x theta, the asymptotic distribution of minus 2 log of lambda x under H converges to a chi-square distribution. The degrees of freedom of this chi-square, they are given by the difference in the number of independent parameters in omega and those in omega h. That means, when we are assuming the parameter space, so we are getting, for example, in the previous problem omega had 4 dimension, mu 1, mu 2, sigma 1 square, sigma 2 square. Under omega h we had 3 independent parameters, because mu 1, mu 2 were independent, but sigma 1 square and sigma 2 square were related. So, there were 3 independent parameters. So, 4 minus 3 will become 1. The number of degrees of freedom for chi square will become. So, basically what we will get in the previous case, for example, minus 2 log lambda x will be converging to chi square 1 distribution. Now, this is a very useful thing, because once the convergence is there, then one need not look for the exact distribution all the time. In certain cases, of course, like in the normal distribution cases, exact distributions we are able to derive, but many times like in the discrete distributions, either we have to deal with the distributions like binomial, Poisson, or we have to look at the spatial tables like we had mentioned about the 2 by 2 contingency tables testing. So, in those cases we can actually consider this approximation, and usually it is considered to be good. More results about these things, they are proved by Wilkes 1937, Rao, he has looked at the asymptotic convergence, the rate of convergence of this, and there are many other authors who have actually considered the limiting distributions. The book of Rao in 1973 discusses in detail, that linear statistical inference book. They discuss in detail the asymptotic properties of the likelihood function. Now, I will consider 2 advanced applications of this likelihood ratio test. So far, whether I was discussing the UMP test, UMP unbiased test, most powerful test, I have considered, you can say, simplistic situations. Generally, I was dealing with the univariate populations or bivariate populations, but in practice there can be even more complex situations. For example, I may have k different populations, and I may like to check whether their means or whether their variances are equal. Now, in this case, certainly the UMP tests or UMP unbiased tests are very difficult to derive. In fact, we cannot write down the form of the joint density function in the form of multi-parameter exponential family, so that this parameter which is to be considered occurs there, and therefore, the likelihood ratio test seems to be a good option. Only thing is, we should be able to derive the maximum likelihood estimators under omega as well as under omega h. So, I will give a couple of examples for applications when we are dealing with multi-parameter situations and the number of populations may be more than 2 also. So, the first one I will do likelihood ratio test for equality of means in one way analysis of variance model. So, the setup is like this: we are having x 1 1 and so on, x 1 n 1. This is a random sample from say normal mu 1 sigma square, x 2 1 and so on, x 2 n 2. This is a random sample from normal mu 2 sigma square and so on, x k 1 and so on, x k n k. That is a random sample from normal mu k sigma square. Note here, I have taken the variances to be common. So, this is actually the situation of a one way analysis of variance model, and we are considering the variances to be the same. Our testing problem is to test that whether the means are the same or not. This is called homogeneity of, that is, means of are homogeneous. That means, the populations are homogeneous basically. If mu i's are the same, then basically it means that we have same population, against that mu i's are not all equal. Now, let me introduce some notation. theta is now mu 1, mu 2, mu k sigma square. So, it is k plus 1 dimensional. I will use the notation x for x 1 1 and so on, x 1 n 1 and so on, x k n k. All the n 1 plus n 2 plus n k observations, that is sigma n I am calling n. These observations I call as x. The parameter space, the full parameter space, if we look at, then the mu I is belong to R, that is k dimensional Euclidean space into positive half of the real line, and under omega h you are dealing with 2 dimensional. Now, the likelihood function is L theta x, that is equal to 1 by sigma square 2 pi to the power n by 2 e to the power minus 1 by 2 sigma square sigma x I j minus mu I square. J is equal to 1 to n I is equal to 1 to k. So, we take the log likelihood here, that is minus n by 2 log 2 pi minus n by 2 log of sigma square minus 1 by 2 sigma square sigma x I j minus mu I square. Now, easily you can see that if I consider the derivative with respect to mu I, then I will get n x I bar minus mu I divided by sigma square. So, this is greater than 0 for mu I less than x I bar, and it is less than 0 if mu I is greater than x I bar. So, you get mu I omega head is equal to x I bar, because the maximum will occur at x I bar. Now, we consider the derivative with respect to sigma square, and I get minus n by 2 sigma square plus 1 by 2 sigma to the power 4 double summation x I j minus mu I square, which I can write as minus n by 2 sigma to the power 4 1 by n double summation x I j minus mu I square minus sigma square. So, once again you can see it is greater than 0 if sigma square is less than 1 by n double summation x I j minus mu I square, and it is less than 0 if sigma square is greater than this. So, obviously, the maximization is occurring at this point, and since mu I is estimated to be x I bar. So, we get sigma omega head square, that is equal to 1 by n double summation x I j minus x I bar square. I give a notation to this. This is equal to S w, that is 1 by n within sample variation, because sigma x I j minus x I bar whole square denotes the variation within the ith sample, and then I am taking sum over all such. So, this is the total variation within each sample I have considered here. So, if I consider L head omega, that is by substituting the values of estimated values of sigma square and mu I get 1 by 2 pi sigma omega head square to the power n by 2 e to the power minus n by 2. Now, for omega h, you are having mu 1 is equal to mu 2 is equal to mu k is equal to say mu. So, this actually becomes a problem of single sample. This reduces to a problem of single sample of n observations. So, mu hat omega h will become simply x bar, that is sigma n I x I bar divided by n, and sigma omega h head square, that will become equal to 1 by n sigma x I j minus x bar square, which I call as 1 by n S t, that is the total variation, okay? Because I am considering the difference of each unit from the grand mean, and then I am taking the sum of squares here. This is the total variation. So, this purpose of writing this S w and S t is to explain the type of terms that we are getting, and this S t you can actually write as double summation x I j minus x bar square here you add and subtract x I bar. So, this gives me x I j minus x I bar plus x I bar minus x bar whole square. So, this becomes sigma x I j minus x I bar square plus sigma n I x I bar minus x bar square. So, this is equal to S w plus S b. Now, this S b, this term is actually variation between samples, because we are considering x I bar, that is the ith sample mean, and x bar is the grand mean. So, this is nothing but the, and then I am taking square and then taking all such cases. So, this is actually how much variation is there between the different samples. So, now we can utilize this and write down the form of L hat omega h. So, that turns out to be simply 1 by 2 pi to the power n by 2 e to the power minus n by 2. So, let us look at these two terms here that we are getting now. L hat omega, here e to the power minus n by 2, and here sigma omega hat square to the power n by 2, where sigma omega hat is the S w by n term. And in L hat omega h I get the same thing, here only omega h is replaced, and the value of omega h that we calculated as S t by n, and this S t I wrote again as S w plus S b. Therefore, the form of the likelihood ratio test, that is lambda x, that is L hat omega h by L hat omega, that becomes equal to sigma omega hat square by sigma omega h hat square to the power n by 2 less than c, which is equivalent to, now by, because of writing down this expression, sigma S w divided by S b plus S w less than C 1. Then you take the reciprocal and subtract 1. So, you get greater than C 2, or we can write S b divided by k minus 1 divided by S w divided by n minus k greater than, say, some C 3. Now, under H, that is mu 1 is equal to mu 2 is equal to mu k, this S b, that is S b by k minus 1 divided by S w by n minus k. This follows F distribution on k minus 1 n minus k degrees of freedom. So, this point C then is nothing but a point on the curve of the density of f k minus 1 n minus k distribution, that is the upper 100 alpha percent point, this probability is alpha. So, then this is f of k minus 1 n minus k alpha. So, this is the usual test which is there in the one way analysis of variance for testing the homogeneity of the means. I will repeat this problem. I made the assumption here that the variances are common, but when we are discussing general sampling from various populations, then many times this assumption needs to be checked. That means, we are not sure whether the variances are also same. If the variances are to be checked, then we can derive a likelihood ratio test for this also. Let me just give a brief sketch of this likelihood ratio test here. Let me consider testing for homogeneity of variances. So, you have seen actually this likelihood ratio test is applicable to very general situations. I considered a k population model and I could actually derive an exact test. Now, here let us consider the sampling x I 1, x I 2, x I k, x I n I. This is from normal mu I sigma I square for I is equal to 1 to k, and the k samples are taken independently. So, our hypothesis is sigma 1 square is equal to sigma 2 square is equal to sigma k square against not all sigma I squares are equal. Our parameter space has become little bit larger. It is actually 2 k dimensional now. The parameter theta is actually mu 1, mu 2, mu k, sigma 1 square, sigma 2 square, sigma k square. The full parameter space is that this mu i's are real numbers and sigma I squares are the positive real numbers, and under omega h it becomes k plus 1 dimensional, because mu i's remain as such, but sigma 1 squares become equal. So, the dimension of this part has reduced to 1. So, this is k. So, k plus 1 dimensional. Now, as before, I will not do the detailed calculations here. The likelihood function that is equal to, since I have to write for the k different populations, I am writing it in this form: product I is equal to 1 to k 1 by root 2 pi sigma I to the power n I e to the power minus 1 by 2 sigma I square sigma x I j minus mu I square, j is equal to 1 to n I. We can simplify this, that is equal to 1 by product sigma I to the power n I 2 pi to the power n by 2, where sigma n I is equal to n, then e to the power minus half sigma x I j minus mu I by sigma I square, I is equal to 1 to k and j is equal to 1 to n I. So, we take the log likelihood function, that is equal to minus n by 2 log of 2 pi minus sigma ni by 2 log of sigma I square minus 1 by 2 sigma I square sigma let me write it as minus half double summation x I j minus mu I square by sigma I square. So, you can easily see that if I consider the usual maximization with respect to mu i's, it will occur at x I bars, and if I do with respect to sigma I square, I will get it at 1 by n I sigma x I j minus x bar square. So, proceeding as in earlier cases, the maximum likelihood estimates of the parameters mu I omega head is equal to x I bar and sigma I omega head square, that is equal to 1 by n I sigma x I j minus x I bar square, j is equal to 1 to n I is equal to 1 to k. Under omega h, that is when we are taking sigma 1 square is equal to sigma 2 square is equal to sigma square, then this L gets modified. L will become minus n by 2 log of 2 pi minus n by 2 log of sigma square minus 1 by 2 sigma square double summation x I j minus mu I square. So, now if we consider the maximization, yields mu I omega h head as before, that is x I bar, but the value of sigma I omega h head square, that becomes 1 by n double summation x I j minus x I bar square. So, L head omega and L head omega h can be calculated. I will write down the simplified expressions here, that is product I is equal to 1 to k 1 by 2 pi to the power n I by 2 sigma I omega head square, a square part we can remove, to the power n I, and then we get, if I write a square here, then n I by 2 I can write e to the power minus n I by 2, that is equal to e to the power minus n by 2 divided by 2 pi to the power n by 2 1 by product sigma I omega head square to the power n I by 2, I is equal to 1 to k, and L head omega h, that is equal to 1 by 2 pi to the power n by 2 e to the power minus n by 2 and sigma omega h head square to the power n by 2. So, lambda x, that is equal to sigma I omega head square product I is equal to 1 to k to the power n I by 2 divided by sigma omega h head square to the power n by 2. So, this less than c, this is equivalent to saying that Now, this sigma I omega hat, that we have already written the expression, that is 1 by n I sigma x I j minus x I bar square to the power n I by 2, product I is equal to 1 to k divided by 1 by n double summation x I j minus x bar x I bar square. This is j is equal to 1 to n I, j is equal to 1 to n I is equal to 1 to k whole to the power n by 2 less than c. So, basically it is in the terms of the sums of squares, and this is, as we have already defined, it is the within sample variance for each sample, and this is the total within sample thing. So, this is coming in terms of the sum of that. Earlier we got 2 dimensional sum, that is S b plus S w thing. Here I am getting k dimensional terms here. The tables, actually the exact distribution of this is not so simple. However, it has been derived, but if we use the asymptotic distribution, that will become chi square on how many degrees of freedom? 2 k minus k plus 1. So, if I consider the asymptotic distribution here of minus 2 log of lambda x, that is chi square on k minus 1 degrees of freedom. So, this was provided by Bartlett in 1937, and the exact tables of this test are provided by R. E. Glasser in 1976 in Journal of American Statistical Association. This part he considered for equal sample sizes, and for unequal sample sizes Chow and R. E. Glasser in 1978 Journal of American Statistical Association. This is for unequal NIs. This test is shown to be unbiased test. So, there are desirable properties of this test that are known. So, if we use this test to check the equality of the variances, and if the equality is there, then we can apply the one way analysis of variance test for mu 1 is equal to mu 2 is equal to mu k. And so, what I have demonstrated here, that the likelihood ratio test gives the solutions here, whereas we cannot directly apply any result for the UMP or UMP unbiased test theory here. Those things are not applicable here. Let me take up another problem here, which is related. Earlier I have explained one problem, testing for independence in a contingency table. Now, in a contingency table you are having 2 attributes, but when we have quantitative data, then how to test the independence. So, the simplest model that we can think of is a bivariate normal population. Now, we know that in a bivariate normal population you have 5 parameters, the means, the 2 means, the 2 variances, and then there is a correlation coefficient, a rho. And it has been it is known that the independence is equivalent to rho being equal to 0. In the bivariate normal population, independence condition and the uncorrelated conditions are the same. So, if we test rho is equal to 0 in a bivariate normal setting, then it becomes the test for independence. Let me show that a likelihood ratio test can be derived here. So, this will be my last example in the likelihood ratio test, and then we will proceed to another theory here. So, testing for independence in bivariate normal distributions. So, let x1 y1 x2 y2 xn yn be a random sample from bivariate normal mu1 mu2 sigma 1 square sigma 2 square rho population. And we want to test the hypothesis whether rho is equal to 0 against rho is not equal to 0. This is the condition for the independence. Our parameter here is the 5 dimensional mu 1 mu 2 sigma 1 square sigma 2 square rho. The full parameter space here is mu i's are real, sigma I squares are positive, and rho lies between -1 and 1. Under the null hypothesis, the dimension becomes 1 less, mu i's and sigma I squares remain the same, however, rho becomes 0. So, the likelihood function here, that is equal to 1 by 2 pi sigma 1 sigma 2 root 1 minus rho square to the power n e to the power minus 1 by 2 1 minus rho square sigma x I minus mu 1 by sigma 1 square plus y I minus mu 2 by sigma 2 square minus 2 rho x I minus mu 1 by sigma 1 y I minus mu 2 by sigma 2. Now, you take the log likelihood here, then that is equal to minus n by 2 log of 2 pi minus n by 2 log of sigma 1 square minus n by 2 log of sigma 2 square minus n by 2 log of 1 minus rho square, and then this expression, that is minus 1 by twice 1 minus rho square sigma x I minus mu 1 square by sigma 1 square plus sigma y I minus mu 2 square by sigma 2 square minus twice rho sigma x I minus mu 1 into y I minus mu 2 divided by sigma 1 sigma 2. Now, if we proceed in the usual fashion for the maximization with respect to the parameters, for mu i's I will get the sample means, and for the sigma I squares we will get the sample variances, and for rho I will get the sample correlation coefficient. So, without getting into too much of the derivations, let me write the final answers here. So, the maximum likelihood estimates for parameters are, so mu 1 omega head, that is equal to x bar, mu 2 omega head is equal to y bar, sigma 1 omega head square is equal to 1 by n sigma x I minus x bar whole square, sigma 2 omega head square is equal to 1 by n sigma y I minus y bar square, and rho head omega, that is equal to r, that is equal to sigma x I minus x bar, let me write a small r here, y I minus y bar divided by square root sigma x I minus x bar square and sigma y I minus y bar square. Now, when rho is equal to 0, then the ML estimates except rho remain same. So, we get then L head omega, that is equal to 1 by one by 2 pi sigma 1 head omega sigma 2 head omega to the power into square root 1 minus r square whole to the power n e to the power minus n. And in L head omega h, except this term, all other things will be same. So, it will become equal to 1 by 2 pi sigma 1 omega head sigma 2 omega head to the power n e to the power minus n. So, the test is simply reducing to. So, the likelihood ratio test is to reject h if lambda x is less than c, which is equivalent to saying 1 minus r square to the power n by 2 is less than c, which is also equivalent to saying modulus r is greater than c 1. Now, under rho is equal to 0, that is under h, the distribution of t, that is root n minus 2 r by root 1 minus r square. This is t on n minus 2 degrees of freedom, and this term is increasing in r. So, we can write the test in terms of t n minus 2. So, basically what we can say, we reject when modulus t is greater than t n minus 2 alpha by 2, because t distribution is symmetric. So, we can consider this alpha by 2 and this probability as alpha by 2 here. This is the acceptance region. So, you can see here also we are able to nicely get the likelihood ratio test for testing for the independence in a bivariate normal population. I have discussed in detail the large sample test, this likelihood ratio test, which is having a large sample optimality property, that is the asymptotic distribution is chi square, and I have derived the exact distributions for testing problems in the normal populations, and also some examples in binomial or exponential distributions also have been worked out. In the next lecture, I will consider another concept, that is of invariance in the testing problems.